Hello, we are the Machine Learning in Real Estate team. This is our demo for Sprint 3. Today, we will touch on the following topics. We will show you a revised MVP. We will go through a recap of the machine learning model BERT we are using in this project. We'll discuss our API and model deployment, a demo of our working model, discuss our approach to data cleanup for training the model, and lastly, our burn down chart and next sprint goals. Here we will show our revised MVP. As a reminder, in Demo 2, we received feedback regarding our project being very open-ended. After receiving this feedback in Demo 2, we've come up with the following MVP vision and goal. To implement and deploy a machine learning microservice onto the BuildUp platform that allows clients to predict construction permit type from a given text description. We've also come up with a proof of concept and improved our solution concept. In this solution concept, you see a client reaching out to our machine learning microservice, which is contained within a Docker container. Within that, we have the web API, and that deploys our machine learning model. And this client communicates to our microservice using a GET request to predict, and we provided a JSON object with text that we want to predict with.
So I'll be going over some of the model revisions we did since our last demo. Again, just to recap, the main part of our model is the BERT model, which was originally developed by Google for language translation. And we took this model and fine-tuned it to use for our specific case. And in the previous iteration, we were able to train the model to achieve 100% accuracy. And that was because we included the permit data type ID in the training data set, which the model was able to recognize and produce 100% accuracy in terms of results. In this revision, we removed all the identifiers in the data, and then we retrained the model on the data without the IDs, and we were able to achieve 90% accuracy, which is a little bit higher compared to 80% accuracy on the research paper that we consulted. And again, this is because the model right now is still currently biased towards the Boston dataset because we only used the Boston dataset to train the model, whereas in the paper they use data from a lot more cities. So that's our next goal, to just retrain the model on a lot more data from different cities. And one of the other changes that we did from version 1 to version 2 is we changed the final activation layer to softmax from Sigmoid. Sigmoid is better for binary classification, and softmax is better for our case, which uses more than 2 output categories.
Now we'll be going over the API and model deployment. In the sprint, we added a new endpoint for the users to send post requests using JSON as the body data, and the data is the descriptions of the permits. And we've been using Postman to pass the body, but this isn't the only service that we can use. And the Flask API framework handles the JSON, passes it to the model, and the model creates an inference and returns a list of possible types of permits. And we've been working on the build-up server, and on the server, we deployed our model and API framework using Docker Image TensorFlow 2.6.0. And we also have a short demo showing the current API endpoint functionality.
So right now our model is being served on one of the build-up servers, and we made a REST API to access the model and make an inference on it. So the model is being hosted on the IP address 51.161.36.102, and it's being exposed on port 5000 under the route predict. And this route expects a post request, and in the data it expects a JSON. And I'll just show you what the JSON expects. So the JSON has a key called instances and a value of a list of strings where each string is an input that the model can make an inference on. So I'll just do that. I'll just clear this and make that post request. And here we see the results being returned. So each one of these categories is what the model thinks the input string best fits under. And we see that these predictions are actually correct. And if you notice, the inputs that we fed into the model no longer has the identifiers associated with them. Last time we demoed this, we noted how the model was able to achieve 100% accuracy because we actually trained the model to recognize the IDs. Here, we retrained the model without the IDs, and we were able to achieve a 90% accuracy, which is surprisingly higher than what we expected, which is great.
Now on to data cleanup. Currently, we're using Boston data for our permit types. We aim to generalize several cities' data in order to train our model with different types of permit data. But due to high variability of permit types within different cities, we're mapping the types into 4 main categories: electrical permit, building permit, mechanical permit, and plumbing permit. This is an example of how we plan to generalize and map the data from different cities, specifically Boston, New York, San Diego, and Austin City. The permit types on the rightmost column of the table are all 14 permit types available within the city of Boston. We have condensed these 14 types into the 4 main types discussed in the previous slide. And we will perform this mapping to the permit data in the other cities in order to train our model further with generalized data, and hopefully it'll become a model that can be used for nationwide data.
This is our sprint 3 burn down chart. We had 46 points scoped for the sprint, and we have 8 points left. And these are our sprint 3 goals. The first is to retrain the model on heterogeneous data. So right now the model has only been fed Boston data. So we want to use data from other cities to create a more generalized model. And we also have server authentication, regroup output categories, start research for image generation job, which would address the other shortcoming on the website, and make route more robust. And this would include checking to see that the user input is in the correct format.